Okay guys, welcome back. So in this video I'll be talking about this will be the last video on waves. So as I mentioned in the last video, I finished talking about the sound and the other concepts that are necessary to understand the concepts on waves. So in this video I'll be focusing only on the concept of stationary waves. Now I explained about the stationary waves in my first video. So in this video I'll be explaining you some examples or practical situations in which stationary waves are used. So to begin with, I'll explain about the introduction again about the stationary waves, because some viewers may have not watched that video. So here's a simple introduction about the stationary waves. So as I mentioned in the first video, a stationary wave is formed when two waves of equal amplitude and frequency travel in opposite directions. So for example, if we have a string like this, if we have a vibrator here which is vibrating at a constant frequency, so if we provide some tension, a constant tension to the string, and we have a barrier here, so what happens when we turn on this vibrator is that since it vibrates at a constant frequency, wave may be formed like this, right? So actually in the original wave we don't have the node and the antinodes, but when this wave reaches this barrier, it is reflected back along the opposite direction, so that the reflected wave is actually the vertical flip of the original wave. So when this wave reaches this point, we can say that we have some loops like this. So it depends upon the place where you place of plucking, or place of changing, or place of displacing, and also it depends upon the length of the string, the number of loops formed. However, in any number of loops formed, you can see that at the zero displacement you have the nodes. So you have the the destructive interference there, and at the maximum displacement, which is the amplitude, you have an antinode. So it will be a combination of nodes, antinodes, nodes, like that up to this point, right? So this is the original wave direction, and the reflected wave is in the other direction. And I explained to you about some characteristics of waves, or actually the stationary wave. So you can see at the antinode that the two waves have the constructive interference. So you can see that here, because at the constructive interference you add up the amplitudes, and at a node the two waves have destructive interference. So as the result of a destructive interference you have a zero displacement here, and the distance between consecutive nodes and the consecutive antinodes, so the distance between these two nodes or these two antinodes is lambda by 2, lambda being the wavelength, right? So it's half the wavelength. You can see that this is half. Now this is full wavelength from this node to this node, so from this node to this node it will be half a wavelength. And also for the distance between a node and the successive antinode, or this antinode and this node, is 1/4 or 1/4 of the wavelength lambda, right? So those are about a general discussion, description, and the general introduction to stationary waves. So let's discuss about some practical situations in which stationary waves, you can see stationary waves. So one of the practical situations where you see stationary waves is the occasion in which we have waves in strings. Now in the first video I explained to you, when you have some string here and you have a barrier here, so when you displace the string up or down like this, a wave is formed. But when this wave reaches the barrier, it reflects back, as I mentioned here. It reflects back like this. Now this is the original wave. It reflects back, and a stationary wave is formed. The speed of this vibration is given by V equals root T over M. So T is the tension, M is the mass per unit length. So you take the ratio of the tension to mass per unit length, and you then take the square root to find the velocity of this vibration, or velocity of the particles of the string, velocity at which these particles move in this direction. So you can find the frequency of the vibration, but if you make this vibration by hand, it's hard to find this vibration. So what we do is we do a simple calculation like this. Although we can't find the frequency if you do manually, what we do is that we know that V equals F lambda. So we can find the velocity by V equals root T over M. So you can find the tension of the string, as well as you can find the total length, and you can find the total mass. So you can divide the total mass by the total length to find mass per unit length. So you know that you can find the value of T, you can find the value of M, so you can find the ratio of T to M, and then you can take the square root to find the velocity of this string, or the velocity of the particles that travel with the string. So you know that v equals f lambda. So furthermore, that you know that if this length is L, if this string is vibrating with the fundamental frequency, you know that one loop is formed here. So at the destructive interference of these bridges, you have nodes, and at the constructive interference, or at the maximum amplitude, or at the maximum displacement, or at the amplitude, you have a node here, an antinode here. So you know that the distance between successive nodes is lambda by 2. So if you take the length of the string to be L, so L, you know that L is equal to lambda by 2. So lambda is equal to 2L. So by v equals f lambda, by substituting to lambda and v, you can find that f is equal to 1 upon 2L times root t over m. So this is the fundamental or the lowest node that can be obtained from the string, right? So it is not. So if you want more frequencies, right, you have to find the overtones. So this slide will explain you what is meant by an overtone. Now if you have a string, you can not only vibrate with the fundamental frequency, you can also vibrate with frequencies that are greater than the fundamental frequency. So those frequencies are called the overtones, right? So when the tension and the other quantities that affect the frequency are arranged, you can say that taking the same string, multiple frequencies can be obtained. So if we have multiple frequencies, the waveform or the behavior or the appearance of the wave or the stationary wave will be changed. So if you plug in the middle, now when you plug a string in the middle, you know that at the point where you plug it, you will get an antinode, right? If you plug at 1/4 the distance, at the place where you plug, that is 1/4 the distance, you have an antinode here. So in this case, I will plug in the middle. So I'll get the fundamental like this, right? Fundamental, you get an antinode here, and you get two nodes at the two bridges or the two barriers. So when you plug with the overtone, right, to get an overtone in the middle, you will get 3 loops, because now you know that this has to be symmetrical. Now if this is an antinode, this can't be in this place, it can't be an antinode. So no, the 3 loops should be formed. So we call this part, this small, right, like the oval like part, we call that a loop. So to maintain the symmetry, now this is symmetrical. If you divide this here, this part will be equal to this part. So to remain symmetrical, 3 loops should be formed. So you have an antinode in the middle, you have 2 nodes in the other ends, and you form 2 nodes to complete the waveform, right? So this is about the symmetric format. So if you have in the second overtone, you should get 5 loops, because to remain symmetrical, you should get 5 loops here, right? So you should get an antinode here, you should get 2 nodes here, and to remain symmetrical, you should get 5 loops here. So I've been explained about the general concept of overtones. When you plug in the middle, let's derive some relationships using the factor that we discussed a little while ago. So to calculate the individual frequencies of the first and second overtones, let's take the general description or the general derivation that I have been talking to you so far. So you cannot actually, it's hard to measure the frequency straight away. So it's always easy to find the wavelength and then derive a relationship actually from the length, and then find the frequency using the fundamental equation v equals f lambda. So for the first overtone, now if this length is L, if the length of this string is L, since 3 loops are formed, now this is a loop, so 3 loops are formed. Now you know that the distance between two successive nodes is lambda by 2, so this distance is lambda by 2. Now this distance is also lambda by 2, and this distance is also lambda by 2. So the total distance is now lambda by 2 times 3, or 3 lambda by 2. So let's take that wavelength to be lambda 1, because I need to calculate the second overtone as well, which I will take the wavelength as lambda 2. So for the first overtone, I will take the wavelength to be lambda 1. So the wavelength, the total wavelength that forms here, actually the total number of loops is 3. So L, which is the length of the string, will be equal to 3 times lambda 1 by 2. So by cross multiplication and solving, you can say that lambda 1 is now equal to 2L by 3. So you know V equals F lambda. So let's take the fundamental frequency F0 and the first overtone as F1, and I'll take the second overtone as F2. So first overtone is F1. So you know that the velocity V equals F1 times lambda 1. F1 times lambda 1. So F1 is now equal to V over lambda 1. Now you know the value of lambda 1. So you can derive that F1 is equal to 3 over 2L times root T over M. So you can find the value of L, you can find the value of T, you can find the value of M. So you can easily find the value of F1. So for the second overtone, we can derive a relationship in a similar way. You can say that since 5 loops are formed, now this distance is lambda by 2, this distance is lambda by 2, so it will be lambda by 2 times 5. So I'll take the wavelength to be lambda 2 now, because it should be different. So the length of the string L is now 5 times lambda 2 by 2. So you can say that lambda 2 is now equal to 2L by 4, right? So F2 is equal to V over lambda 2. So you can finalize that F2 is now equal to 5 over 2L times root T over M, right? So furthermore, you can identify another relationship between F0, F1 and F2. You know that this F0 is now equal to 1 over 2L times root T over M. F2 is equal to, F1 is equal to 3 over 2L times root T over M, and F2 is equal to 5 over 2L times root T over M. Now observe this 1 over 2L times root T over M here, F here. What we have done here actually is that we have multiplied that by 3 here. So 3 times 1 over 2L times root T over M is equal to F1, and at F2 we have multiplied that by 5. So that will be 5 times 1 over 2L times root T over M, which is 5 times F0. So we can say that F1 is now equal to 3 times F0 and F2 is equal to 5 times F0. Now 3 and 5 are both integers, so we can conclude that overtones are integer multiples of the fundamental frequency for a particular wave. So we don't require the wave to be whether the required wave or the wave we have considered to be plugged at the middle or at a distance of 1/8 of the wavelength or at 1/4 of the wavelength or even 3/4 of the wavelength. We don't need to consider whether it's actually where it was plugged, right? Whether it's in the middle or at any point of the string. The overtones for any waveform will be integer multiples as follows. Now this integer multiple 3 and 5 may change when you are plugged in at some distance away from the middle. However, you can take that you have integer multiples of the fundamental frequency for any wave. So that's it about the waves in strings. So as the second part of this video, let me explain you about waves in pipes. So waves in pipes are similar to waves in strings. The only difference is that at pipes are, unlike in strings, are classified as closed pipes and open pipes. So let's identify what is meant by a closed pipe and what is meant by an open pipe. Now if you have here, for example, see that at the end of a barrier you can see that there's a node here, and at the end at the maximum displacement you have an antinode. So that's the concept that we'll be using in pipes also. So at the closed end of a closed pipe, where actually a node is formed, and at the open end you have the maximum displacement, which is the amplitude, so an antinode is formed. So this is in direct contrast to an open pipe in which we have both ends opened, so there are no closed ends, so you cannot see antinodes at both ends. You can see antinodes only at the middle of the wave, middle of the pipe or middle of the wave. So at both ends you can see that the particles vibrate with the maximum displacement, which is the amplitude. So antinodes are formed at both ends. So having explained about the general characteristics of the waveform in closed pipes and the open pipes, let's investigate about the wave formation, the fundamental frequency and the overtones of closed pipes separately and open pipes separately. So first of all, let me take the closed pipe. When a closed pipe is vibrating at the fundamental frequency, you can see a wave pattern as follows, right? wave pattern as follows. So you have a node here, right, and an antinode. So you know at the barrier the particles move with the zero displacement. At an antinode, particles move with the maximum displacement. So you have the amplitude for the wave here. So a wave pattern as so it should be formed. Now you know that the distance between the node and the successive antinode is lambda by 4. So if you take the length of the pipe to be L, you can say that if the wavelength is lambda 1 by 4 should be equal to L. So lambda 1 is equal to 4L. So the fundamental frequency F0 is now equal to V by 4L, right? So as in the waves of strings, overtones can be obtained for closed pipes. So they are like this. So if you have the first overtone to remain symmetric, you have an antinode here, you have a node here. So a wave pattern as follows should be formed. So we actually derive these wave patterns to make the number of nodes and antinodes as minimum as possible. Now you can say that now this wave pattern should be the first overtone. It's correct because you should have a node here and you should have an antinode here. So you should have some loops here. But we take the waveform, the number of nodes and the antinodes to be minimum, to remain symmetric. So that's the most important concept when you draw wave patterns in strings, in open pipes and even closed pipes. So we take the minimum number of nodes and the antinodes to remain symmetric. So the first overtone should be something like this, not something like this, right? So an antinode is formed here, a node is formed here. So now this is a node, this is a node, and this is an antinode. So you know that the distance between two successive nodes is lambda by 2, and the distance between a successive node and an antinode is lambda by 4. So this distance will be lambda by 2 plus lambda by 4, which is 3 lambda by 4. So 3 lambda by 4 will be now equal to L, which is the distance from the closed end to the open end here. So lambda 1 is equal to 4L by 3, right, by cross multiplication. So you know that F1 is equal to V by lambda 1. So F1 will be equal to, by solving, 4V by 3L. Now we know that F0 is V by 4L, right? So V by 4L. So you can say that F1 is equal to 3 times F0, right? So similarly, for the second overtone, you can say that this distance, right? This distance is now lambda by 2, this distance is lambda by 2, so that will be lambda times this distance is lambda by 4, that will be lambda plus lambda by 4, which is 5 lambda by 4. So 5 lambda by 4 is equal to lambda 2 here. So F2 is equal to V by lambda 2. So you can finally say that F2 is equal to 5V by 4L. So F2 is now equal to F0. So as in the case of strings, the overtones of a pipe or a closed pipe or even an open pipe, when I discuss a little time later, you will notice that even in an open pipe, that the overtones are integer multiples of the fundamental frequency. So having discussed about the closed pipe, let me introduce about the open pipe. So as I mentioned a little while ago, in an open pipe both ends experience antinodes, right? So it should be as so, because you know at a barrier you get the nodes, and at some free end you get particles to vibrate with the maximum displacement or with the amplitude. So antinodes are formed at both ends. So a node should be formed when it is actually vibrating with the fundamental frequency at the middle of the open pipe, right? So if the wavelength, if the length of the pipe is L, you can say now the distance between two successive antinodes is lambda by 2. So lambda by 2 is equal to L. So lambda is equal to 2L. So the fundamental frequency, which is F0 equals V by lambda, will be V by 2L, right? So overtones, as in the case of strings and closed pipes, will be integer multiples of the fundamental frequency. So you can observe the wave patterns like this. To remain symmetric, you have to form antinodes here at both ends, and at the first overtone you have to take the minimum number of nodes and the antinodes to complete this symmetry. and remain the antinodes and the nodes at the ends, right? So you will get the first overtone like this. So the distance actually, now this part and this part correspond to one loop. You can see that now this part and this part is equal to this part, so that will be two loops. So when you form two loops, you know that you will form one wavelength. So if the length of the pipe is L, you can say that the length of the pipe is now equal to the wavelength. So since F is equal to V by lambda, you can say F1 is equal to V by L. However, you know that F0 is equal to V by 2L, so F0, 2 times F0 is equal to 2 times V by 2L, which is V by L. So F1 is equal to now, F1 is equal to now 2 times F0. Similarly, you can find a relationship for F2, and you can conclude that F2 is equal to 3 times F0. Now if you, now unlike in the strings, you can only obtain these wavelengths and these waveforms and the characteristics of waves in open pipes, because you know that you can pluck in the middle, or you can pluck at the ends, or you can pluck at the distance, some distance you want. So you can only vibrate with a constant frequency here, either at the open ends, either at this end or in this end, and in the closed pipe at these ends, right? So the only wave pattern that can form inside, unlike in the case of a string, only wave pattern that can form inside a closed pipe here, here, here and here are as follows. So you can find not even the second overtone, you can go to third overtone, fourth overtone, and so on. So you can find the frequencies as so on. And one final important concept of pipes is that the end correction of pipes. So you know that when you have a closed pipe like this or an open pipe here, what happens is that the air, the open pipe, end of a pipe, either when it is a closed pipe or an open pipe, is free to move, right? Now in the case of string, you had some barrier here, you had a string like this. But in the case of pipes, there is no barrier at the open end, right? So when you take a string, you at one end you plug the string, or you swayed it up or down, or you used a constant vibrator to do that. So that's actually a closed end. It's like a closed end of a pipe. And at the other end, you tied it to some place, some barrier, some wall or somewhere, so that the string is reflected back to form the stationary waves. However, in the case of pipes, either in the closed pipe, at the open end of a closed pipe, or at both ends of an open pipe, there's no barrier, right? So you cannot say that the string, as in the case of a string, the waveform will stop here or will terminate its progression here. So practically one see that this waveform generally goes above, right? Now in the case if you have it is horizontal, right? If it is horizontal like this, it will go beyond. It will go beyond this part, right? Somewhere here. So what actually happens is that there will be a small part that will be hanging like this. So we call that the end correction, right? Because there is a part that will, however, although we have some part like this, we don't actually, when you are calculating the frequencies like this, we don't take that part we'll call E, because it is the end correction, that part into account. So that's so what you do here, we take pipe, you total length in the subject, you take the subject as not L plus but L plus E, because we have only one end correction to be added. And in the case of an open pipe, you take both parts, right? Both parts, so that the total length will be L plus E, right? L, which is this distance, plus E, which is equal to L plus 2E. So lambda by 4, when it is vibrating with the fundamental frequency, will be equal to L plus E. So lambda is equal to 4 times L plus E. So in an open pipe, lambda by 2 is equal to L plus 2E. So lambda will be equal to 2 times L plus 2E. So you know the wavelengths for the closed pipe and the open pipes when it is vibrating with the fundamental frequency. So we can find the frequencies, fundamental frequencies for a closed pipe and the open pipe accordingly when considering about the end correction. So one important thing is that the experiment really shows that is approximately 0.3d. So 0.3d is actually, the d is the distance between here. So distance, the d is the diameter. Now you know that the pipe is not actually a rectangular part. Pipe is actually a cylindrical part, right? You can do the experiment in a lab, you can find those practically. So you know that this is actually a cylindrical one. This, although I draw in 2 dimensions as a rectangular part, a pipe is actually cylindrical in 3D. So what actually happens is that you have not width here, you have the diameter of a circular surface or a circular area. So let that diameter be d, so you can find experimentally that is approximately 0.3d, right? So those are about the important facts that I explained in this video and in the concepts of waves in strings and pipes. So that's it. In this video, from this video onwards, I will be focusing on another topic of physics, which is heat. So thanks for watching this video and see you soon.